Hello, today I'm gonna show you how you can implement one type of reaction diffusion mathematical equations, which is called Gray-Scott model. And I found a good website which explains what it does, how you can calculate using mathematical equations. So I'm gonna make a implementation for Houdini based on this explanations. So let me do that. Okay. First of all, you need to have some parameters. So basically, you need to make a geometry first. Delete the file, and I'm gonna first creating a null first to have all the parameters that I want to control. Okay. And I'm gonna make a parameters here. Okay, first of all, I would like to have, since I'm gonna make a 2D reaction diffusion patterns, so I'm gonna use a grid as a base. So first of all, the size of the grid. Yeah, and from 0 to 10 is fine, integer, and the resolution of the grid. How many divisions you want to give, maybe maximum 500, could be more. And also you would want to have a starting patterns when you do a reaction diffusion. So let's make it as a circle, and you want to know how many circles you want to plot as a initial state. So I'm gonna name it start nums. Could be from 0 to 10. Yeah. And also I would like to set the radius for those circles. So I'm gonna use a minimum radius plus maximum radius so that you can gradually have a circle drawn on the surface, on the grid. So max rad, and could be from 0 to around 3 probably. Yeah. Okay, so here comes the parameters for the reaction diffusions. Let's see what kind of parameters that I need. So simply, basically you will have two elements in one pixel. In terms of this, one is A, which with a chemical A, which is another one is a chemical B. The chemical A is added at a given feed rate, and the A and B reacts together. A will be feeded as a food by B, but B itself will kill himself by some kill rate. Yeah, and as I can see, when you visualize those two together, it's kind of using the ratio of A or B, otherwise of B, in order to draw this pattern, I guess. So I guess I could just draw either one of it, since if A is more, it looks yellowish here, or whitish here. If B is greater than A, then it will look darker color, could be black. So the A and B should be a different types of value, basically, and you want to calculate each A and B by timeline. So each frame you want to feed this A, add A with the calculated value here, B as well, and the reaction diffusion rate will be determined by the value of the current A, B, as well as this Laplacian functions for 2D, which is like kind of a smooth function. So I could also write that in code, I guess. Now the parameter is it's this one, dA, dB, F, and K. So dA and dB is A rates for A and B, diffusion rates. So I guess if this is bigger, then the diffusion rate is higher. The diffusion could go faster if it's bigger, I guess. And if the F is a feed rate, so the speed how fast the A will grow up or generated. The K is a kill rate for the B, so the greater the K is, the B will be killed faster. Okay, so you would want 4 parameters here, dA, dB, F, and K. And also if you want to control the speed of the diffusion overall, then you could have another parameters called delta T. Could be from 0 to 1, I guess. So in total you'll have 5 parameters, so let's have that. First of all, dA, the range could go from 0 to 1, dB, dB, also from 0 to 1, and F. This one could be around 0 to 0.1. K could be from 0 to 0 to 1 as well. 0.1. And last of all, delta, which is the speed of the diffusion, the reaction diffusion, could be around 0 to 1. And all is float numbers. Right now I got the parameters here. Let's set a default parameters. The size could be 10, resolution could be like 250 for now, and stop numbers, I don't know, around 5, mid, radians could be 0.5, 0.6, 0.4, and dA could be 1, dB could be 0.5. I'm just copying the value from here right now. The F could be 0.055, and the K could be 0.062, and the delta could be just 1. And let's start making it. First of all, you need a grid in order to simulate the reaction diffusion, and you can refer to the size here. Copy this parameter and paste it here, size. Okay, and also the resolution. Copy this parameter, pasted it to rows and columns, and see if I can get the, yeah, now I get the 250 resolutions grids. And next I would like to set where would the initial circles will be placed. So, well, I'm gonna use a point wrangle and make it to detail, and I'm gonna import the number, start number from the controller, which I named start nones. So since I have around 5, I can iterate through this number like this and make a random index out of whole points on the grid, which can be done like n random times n points. Okay, and use that index to set the group, call start. Now if let's name this initialize. Let's look at the geometry spreadsheet. So I have 5 start point. Set it as a group. Okay, that's good. Now let's try to set the circle on that point. Now I would make another point wrangle. Let me say circle, and let's draw. Okay, first of all, what I would like to do is to get the first of all, I'll just name this initialize to. First of all, in order to do a Laplacian filters, Laplacian 2D calculations afterwards, what you want to have is that if you're looking at this point, you want to know what's the neighbors. Like based on this point, you have 4 adjacent neighbors and 4 diagonal neighbors. So you would want to get that one. You would want to get those informations based on the position of the point. Well, the easiest thing, I guess you could just use like near points functions, but I will attach an attribute to each point with the value, the attribute named u and v, so that you can just refer to that attribute whether its point is on the what number on u and what number on v. It's like the index for the u direction and index for the v direction. Okay, now simply enough you can just write like this. For the u, you can get the current number of the point, current index of the point, divided by CHF controller resolution. And for the v, you can get the current number, module CHI controller resolution. Okay, that's it. And let me check, and you have u and v. And if you want to check if it's correctly used as a address for the u direction and v direction, you can make a marker here with the attribute u, could be a text, close, and it's pretty small, but okay, so this direction is the u, so you can see that the number is incremented by 1 for this direction for u, and if I add v, Let's color this red. Now in this case, from this direction is for the V. So the number V is incremented by 1 in this direction. So I guess what I'm doing is correct. I'm just gonna hide this and let's continue. Now I'll, as I said, I would like to make a information for drawing the circles as an initial state pattern. So first of all, I'm gonna import the parameters from the controller. Controller min rad, yeah, and the float max rad. Okay, and also you would like to get a new point from the start group. Oh, to the start group. With the current position. So if you have like 4 start point, and if you look at from each points, you want to know which start point is, start group is closer or nearest. That's what it's doing here. And by that you would get the closest distance to the start point using distance from P to the near point index. Okay. And now you got the distance, you would like to probably clamp the distance by the min radius and the max radius. Okay, and use dot value and to apply to the attribute called color so that you can use it to color the mesh afterwards. So I'm gonna fit that distance value from min rad, which is the minimum, and max rad, which is the current maximum radius, to 0 to 1. And that's about it. Let me check. Okay. Okay, so there's also an information here on this website, reaction diffusion tutorial called Sims. On here, the grids is initialized with A equal 1, B equal 0, and small areas seeded with B equal 1. So most of the place are initialized with A equals to 1, and just some part is initialized with the value B equals 1, which means I guess the B stands for the circle that I am just trying to draw. So what I could do, I could make an attribute A, which is a distance, or simply the same color as the col, which I have just made here. And for the B, I could just do the other side. So from min radius to the max radius as a source domain could go from 1.0 to 0. So the closer it is to the center of the radius, center of the circle, the higher the B value is. That's what I'm doing here. Now let's check if the color is attached correctly. I'm gonna use a call attribute, and yeah, it's showing as I'm expected. I'm gonna hide the grid for now, and let's try to change parameters here. So if I change the size, it will change the size of the grid. If I change the resolution, it will change the resolution of the grid. And if I change the start numbers, it changes how many initial circles you will have. As well, if you change the minimum radius, you can change the gradational patterns of the circle, the initial circle. Now the problem is you cannot just have the same value here and here, because it doesn't accept the fit functions, so it's gotta be somehow different, but I guess that's okay for now. Okay, so let me do like this as an initial value. It's fine. And 5 in its initial value. Okay, now this is enough for the initializing, so now it's time to do some reaction diffusion simulations, and I will need a solver. Now let's get inside here, and what I'm gonna do is pretty much simple. I'm just gonna use point triangle and just implement a equations which is explained here, and that's pretty simple. So let's do that. First of all, let's open the bigger editor screen here, since I'm gonna write a little bit long script. So first of all, let's import some attribute, float A from float B from the point attribute, and float F is CHF, controller F, and I'm gonna copy this, and also I will have a K, and also a DA and DB, DB, DA, DB, and also a delta. Yep. Now, I guess that's all for the parameters that I can import. Now, what I also need is a Laplacian to the Laplacian functions, which I have to implement by myself using Vex script. So let me write that one first. Now, first of all, I would need a little function called get pt index. Now see that when you wanna get the the neighbors determined by the number of u and number of v, you want to get the real index of that points based on the Houdini's data structure. So that's what I want to have. So if you have an input u and v as an index, what you want to get is a index, the final index, which can be calculated as u times controller resolution plus v. and this will give you a final index position index for the points, which is in the Houdini data structures based on the u and v value of that point. Okay, also, and finally you can get the Laplacian functions, and since you would want to get two values, one is for the a and one is for the b, so you would need two Laplacian outputs. So as an output, I could get a vector 2, which is same as the float 2, and get, I'll name this get Laplacian 2D, and as an input you want to input u and v, which determines which points, the address of the points, and also now in order to calculate the 2D Laplacian, you would have to use 3 times 3 kernel, which the number is different if the point is placed on the center of 3 times 3 grid. If it's on the center, I will use a center value. If it's on the adjacent neighbors, I'll use the adjacent value, and if it's on the diagonal corners, I'm gonna use diagonal as a parameter. Now I guess this page doesn't really explains about the Laplacian 2D functions, so you gotta go to the other page in order to understand what that really means. I guess if you search the web for Laplacian 2D, you will find what it is. But basically, it's the kernel function that is used to smoothen the value of the current value, like a or b, based on the neighbor value. So if the neighbor value is low, even though your self is pretty high, the current value, the value yourself will get lower based on the value that is on the neighbors. And since adjacent neighbors are closer than the diagonal neighbors, adjacent neighbors are the influence of the adjacent neighbors are stronger than the diagonal corners. Yeah, this is where it explains how it is. So the center weight is -1, the adjacent neighbors 0.2, the diagonal is 0.05. Since you have 4 adjacent numbers, the total will be 0.8 for the adjacent neighbors, and for the diagonal you also have 4, so the total number will be 0.2. So 0.8 plus 0.2 equals 1, which is the same value as the center weight. And this is how you can smoothen the center value by adding the smoothened value to the current value. Well, it's better to understand, to write the code to understand by yourself, I guess. So let's just write it down. Now, first of all, you gotta import the parameter from the controller up above inside the controller, the resolution, and let's make a vector 2 new Laplacian, set to be 0. Okay, and return this Laplacian as a final result. Now this is where you need calculations. Okay, so first of all, you gotta make sure that the UMB is not on the corner, since the corner index, corner points, doesn't have a 8 neighbors, so you cannot really calculate the correct Laplacian on the corner. So first of all, I'll make a condition to ignore the corner points. So u minus 1 must be greater than 0, and u plus 1 less than resolution, v minus 1 is larger than 0, v plus 1 less than resolution. Okay, that's the condition that you need, and now you can make a 2 for loop. 1 could start from minus 1 to 1, increment it by 1. Another for loop from minus 1 to 1 and increment it by 1 as well. And now, based on the I and n and u and v, you can get an index of the neighbor points, including yourself, using get pt index, which you made it here as a function, and write it like this. UNI will be the x index, and v and n will be the y index. Now the final the current Laplacian, well, it's not, I would say AB will be vector 2, AB will be set 0.0. So you want to get the A value on this index for the first one, for the x value of this vector, and for the y value of this AB vector, you want to get the B value like this. Now this is where you're gonna use the center, adjacent, and diagonal parameter, which is in this case -1, 0.2, and 0.05. If I equals to 0 and n equals to 0, which means it's on the center, you would wanna multiply this AB times center. Now else if absolute of I plus absolute of n, and which is moduled by 2 equals to 1. This means that it is on the adjacent position, so ulap will be AB times adjacent parameter, in this case 0.2. Else, use the diagonal. Okay, let me check if this is correct. If I apply, I get an error. And where it is. Okay, this has to be N. And I still have an error. Check. Valid source. Okay. Am I doing something wrong? Okay. I'm making vector true, but I'm using 3 parameters here, which is weird. Okay, this is good. Now I have made a Laplacian functions like this. Finally, I can combine all those together to actually calculate the diffusion reaction value, reaction diffusion value. Okay. Now both equations is using a times b power of 2 for b, so I'm gonna make a temporal variable co-reaction is equals to a times power b of 2. Okay, and the updated a will be dA times Laplacian AB. Oops. I also need to get the Laplacian AV using the function that I have just made. Based on the current u and v, and the center parameter is -1, adjacent is 0.2, and the diagonal is 0.05. Okay, so the updated A will be dA times Laplacian AP. And since I'm using the Laplacian, the first value of the Laplacian, which is for the A, I'm gonna just get the index of 0 and minus reaction plus F times 0.1 minus A times delta for final speed. Now let's check. So dA times Laplacian A minus reaction, which is A times B, plus F times 1 minus A, and finally multiply by delta. Okay, so that's good for A and B. dB Laplacian AB is the second value on the Laplacian vectors, and plus reaction minus K plus F and times B and times delta as a final value. Okay, so dB times Laplacian B plus reaction minus K plus F times B times delta. Yes, seems correct. Okay, so apply this, accept, and inside the solver, that's all I need to do. So go back, and right now it's supposed to update the value A and value B, but I really cannot see it by the value here since I'm not using A or B for the visualizing. So let's visualize it so that you can easily see what's going on with this reaction diffusion. So what I would like to do, I would like to give a 2.5D visualization. So I just wanna extrude the black part to the upward, to the y direction, so that I can get some mountain view of the reaction pattern. So that will be pretty easy. I'm just gonna use point wrangle here and just draw y equals to no, just use a, which is from 0 to 1.0, and if a is high, then give it a 0 value, and if a is low, which is on the black part, give it a high position. Yeah, like this. And after all, and finally, let's update the color as well based on a value or v value. I'm gonna just use the a. So type a as an attribute and bring this color a little bit to the right, the black part to the right, I guess, and see how it goes. And I can see something is happening, but the reaction speed is a bit slow, I guess. So what I can do, since the delta is maximum 1 right now, so I cannot increase this larger than this or it's just gonna explode. So I'm gonna just increase the sub steps like to 50 or 30 and try to calculate that. And now I can see a pattern is being generated using the parameter f, k, and dA and dB. It's pretty interesting. Now let's change this to 45 and let's change some parameters to see a different type of patterns. Now if you go to the website or many website, they introduce you with many types of parameters like these. So let me type some parameters that will make the pattern a bit interesting, like the current one. Now if I type f to be 0.04 and k to be 0.06, and if I play it, we'll make, yeah, it's more like a synchronous patterns. If I make it like 2, you see it's more symmetrical. Very interesting, yes. Okay, now if I type this to be not this one, the f to be 0.035 and 0.065, change this to round 4. Well, I guess the reason why it just disappeared like this, I guess the diffusion rate for the B is too fast to kill those pattern too fast. So let me change dB to be 0.5, play it, and now I can see another interesting pattern which like split it's spot like a cell division, like log egg. And yeah, it's pretty interesting. Okay, now the other pattern, which is also famous, I'll give this back to 0.5, and the other one, the f equals to 0.012 and k equals to 0.05. Now, what would happen? Now this one gives like a never-ending wavy pattern, which is also pretty interesting. Yeah. And okay, last one I would like to try, 0.025 and 0.05. Now this gives me more like a wavy patterns. Maybe I could lower the dB a little bit. Start from the beginning. Maybe I could adjust the height a little bit. I don't know. Could be from minus 1.0. Well, it doesn't make any difference, I guess. All the colors. Yeah, but still, I mean, looks interesting. Maybe I need more resolution for this pattern, since I'm using 250 by 250 right now. If I increase this to like 400, redo the simulations, yeah, looks more interesting. Yes, kind of a dissolving. Yeah, I guess I need to fine-tune these parameters in order to get the interesting geometry. But that's how you can implement the reaction diffusion equations called Gray-Scott model, and based on the mathematical equations. And I hope you find it interesting. And actually, if you change the Laplacian 2D function to 3D, you can also apply this to the voxel, 3D voxel as well. I also tried that one before, and of course the calculation is a bit slow, but it's also pretty interesting to try with. So yeah, hope you can try that yourself as well. If you want to see that, I can make a video for that as well, if there's any needs. This one's pretty interesting. Okay, that's it. That's about it. So thank you very much, and the HIP file is in the video description as always. Okay. Yeah, cool. Thank you.